Hi, 8th grade. Today is Thursday's lesson, and today we're going to be doing lesson 7-6. That starts on page 447, and today's lesson is on exponential functions, so this is something that is brand new. We're going to be working on an example from problem 2 today, and then your gotta check is going to be page 448, number 2, so we'll get to that in a second. Your homework for today is going to be on page 450, numbers 10 to 18, and your bell ringer today is page 439, number 23. Don't forget to do your sentences. Okay, let's get started. So an exponential function is something really new. We've never done exponential functions before, so this is going to be kind of fun. Because they're exponential functions, this is going to be our first time doing a function where we have a variable as an exponent. So this is exponential functions. Okay, exponential functions always follow the same pattern, okay? They always follow the form y equals a times b to the x power, okay? Now, they do make some stipulations here. So first of all, they say a can never be 0, all right? It can be 1, but it can't be 0, and that makes sense. Otherwise, we just get a straight line because we're multiplying y equals 0, so that's no fun, okay? They also tell us that b cannot equal 1, okay? And that makes sense because 1 raised to any power, it doesn't matter what power it is just 1. So again, we get a straight line, and we can't have that happening, okay? Also, b must be positive, okay? And this is because when you raise negatives to negative numbers to a power, when you raise them to an even numbered power, your answer is positive, but when you raise them to an odd number, your number is negative. So we'd end up with kind of a goofy looking graph that would go back and forth. It wouldn't make any sense. So our b has to be positive, okay? All right, I'm going to show you two types of exponential functions. So the first exponential function I'm going to show you is a function for exponential growth. And we're also going to do exponential decay. So I'm going to write those two on both sides, and we're going to sort of compare and contrast them. Okay, so an example of an exponential growth function would be something like y equals 2 to the x power. Okay, now some of you might be saying, well, where's the a? I don't see an a or anything multiplied, but our a is actually 1. And most of the time with mathematicians, if you're multiplying something by 1, you just put that 1 away and you don't write it, because anything minus 1 anything multiplied by 1 is itself, so they leave that alone, okay? If I was going to show what my graph of an exponential function would look like, okay, my graph of this particular exponential function would look kind of like this. And the reason they call it an exponential function is because as x gets larger, it grows exponentially, okay? So exponential functions model exponential growth. They start out really small, okay, close to 0, but not quite at 0, and then they grow exponentially, okay? So in this case, the reason it's exponential growth is because this number, my b, is greater than 1. So when your number that's raised to the exponent is greater than 1, you're going to have an exponential growth function. Let's take a look at an exponential decay function. So an exponential decay function would be something like, for example, y equals 1/2 raised to the x power, okay? So in this case, you can see that my b is different. In this case, my b is less than 1. So I have b is less than 1, but my b is also greater than 0, right? Okay, so b is less than 1, but b is also greater than 0. So it's kind of in between. Okay, so when my b is a fraction or a decimal that's less than 1, I get an exponential decay function. So let's take a look briefly at what those look like. If I was going to draw this one out, okay, my exponential decay function would look something like this. And that means that my numbers are going down exponentially. So what's going to happen is the bigger x gets, it's going to get closer and closer and closer and closer and closer to 0, but it's never going to quite touch. All right, and that's what makes it exponential decay. It's getting smaller and smaller and smaller and smaller, but it's never going to quite get to 0. Okay? Let's try an example problem using an exponential function. So remember when I said we're going to work mostly on problem number 2? And problem number 2 is on page 448, so you might have to turn the page there. Okay. Problem number 2 gives us the function, and it says our function of x is that we have 30 flower beetles, and our flower beetles are left undisturbed in a warehouse bin. The beetle population doubles every week. So I have a starting amount of 30 beetles, and it doubles every week. So this is my start value, and this is the rate at which it doubles, okay? So what they want to know is, they're telling me that x is the number of weeks, and they want to know how many beetles will there be after 56 days. All right, so this is an interesting problem, okay? What I need to find is the number of weeks, right? Once I find the number of weeks, I can just plug that in for x, okay? But I don't know the number of weeks, I know the number of days. So the first thing I have to find is the number of weeks. So my number of weeks is going to equal 56 days, and I'm going to need to divide that by the number of days in a week. So that's 7. So 56 divided by 7, that would be 8 weeks. Okay, hooray. So now that I have the number of weeks, now I can plug this in for x, and I can find out what this function would equal. So my function equals 30 times 2 to the 8th power, and 2 to the 8th power is equal to 256. So now I have 30 times 256. And 30 times 256 gives us a big number. That is 7,680 beetles. That's a lot of beetles, okay? I certainly wouldn't be responsible for clearing out that warehouse after 8 weeks, okay? So, time to try our gotta check. So, our gotta check is problem number 2. So we're doing gotta check 2, and that's also on page 448. So it says an initial population of 20 rabbits triples every half year. So our function is an initial population, so our start value of 20 rabbits is going to triple. That's our rate. And it says that x is every half year, so x is a half year. And what it wants to know is how many rabbits will there be after 3 years? Okay, it's time to pause the video. When we come back, I'll give you the solution. All right, let's try gotta check number 2 together, okay? So when we look at this, okay, x is every half year. So they give us every 3 years, so that really doesn't help us in finding out how many half years. So in 3 years, there are 6 half years, okay? And again, I could just take 3 divided by a half, okay, or 3 times 2, but that would give me 6. There are 6 half years. So 6 is the number that I'm going to have to plug in for x into my function. So my f of x equals 20 times 3 to the 6th power. Now, 3 to the 6th number is a really gigantic number. This is the point where you want to get out your calculator. So if I get out my calculator, 20 times 3 to the 6th power, that is 14,580 rabbits. That's a lot of rabbits, folks. But this is exponential growth, so that does make sense. Okay. Hopefully you got that, and it is time to try your homework. So your homework for today is page 450, numbers 10 to 18, and your bell ringer and 3 sentences, page 439, number 23. All right, goodbye. Tomorrow we'll take a little bit more of a look at graphs of exponential functions.